All right, well, how about we get going here? Well, so welcome everyone to the 33rd Quarterly Northeast Digestion Roundtable meeting. NEBRA's been hosting since April 2016. We've been supporting these roundtables to kind of share technical operational experiences and advance best practices for anaerobic digestion. It's not a webinar, it's more of a meeting or a roundtable format, so a little more informal. We're going to have a presentation by Chad Whiting from MWRA, and then we're going to open it up for questions and discussion. And he's actually perfectly fine with you interrupting him with questions. So I'm going to ask you just to stay on mute during the presentation. Raise your hand or come off mute. I'll see you and we can ask you to ask your question. There's also a chat function. Feel free to use that when you think of the question. So I'm recording this and it'll get sent out next week with the slide deck as well. So I first want to start out by giving a shout out to our sponsor for today's webinar, CDM Smith. They are a longtime contributing member of NEBRA. CDM Smith is a consulting, engineering, construction, and operations firm delivering exceptional service to the public and private clients worldwide. They help clients like MWRA to implement biosolids treatment, disposal, and beneficial use options utilizing the latest thickening, stabilization, dewatering, composting, thermal drying, incineration, and odor control technologies. And I did see a couple of CDMers in the meeting here, so shout out to CDM. Our speaker today is Chad Whiting. He's the Deputy Director of Operations for the Massachusetts Water Resources Authority. He's working out of Deer Island Treatment Facility there in Boston Harbor. He's a seasoned public utility leader with over 2 decades of progressive experience in water and wastewater operations and management and regulatory compliance. Progressive is right. Deer Island Treatment Plant is the second largest wastewater treatment facility in the United States. Prior to this role, Chad served as MWRA's Manager of Wastewater Operations. He also previously held leadership positions with the City of Somerville and with the town of Plymouth, Massachusetts. And prior to that, Veolia, Earth Source, and Earth Tech. He's a licensed operator, both drinking water and wastewater in Massachusetts. And he has a BS in engineering technology from Wentworth Institute of Technology. I know he's excited to present today, so we're going to get going. And Chad, you can take over sharing the screen and I'll stop.
Excellent. Can you see my presentation?
You can.
Excellent. Yep. Janine, thank you for inviting me today. I'm honored to be here to present at the Anaerobic Digestion Roundtable and have an informative discussion about poo to pellets, a regional approach to beneficial reuse.
All right.
All right. Yeah. All right. Here we go. Next. So this is a map of the MWRA service area. We are a regional wholesale provider of water and wastewater services to the residents of Massachusetts. On the water side, we have 61 communities, about 42% of the Massachusetts population, about 3.1 million people. We deliver about 200 million gallons per day of clean drinking water. We're voted the best tasting water in the country for the last couple of years. In our wastewater service area, we have 43 communities, about 2.3 million people, and we receive about 360 million gallons a day average flow. So we have significant I&I problems, about 50% I&I from 4 combined communities: Boston, Cambridge, Somerville, and Chelsea. MWRA has spent over $1 billion in our dedicated, detailed CSO control plan. MWRA also owns and operates the Clinton Advanced Wastewater Treatment Plant in Clinton, Massachusetts. This plant serves the communities of Clinton and Lancaster. This advanced wastewater treatment facility protects the watershed in this area. Deer Island is the ultimate recycling facility, sustainably developed on 210 acres, built to withstand a sea level rise of 2.5 feet. There are 60 acres of public access trails around the island, offering amazing views of Boston Harbor and Massachusetts Bay. Deer Island is the result of a $3.8 billion construction project to facilitate the cleanup of Boston Harbor. Deer Island has a peak capacity of 1.3 billion gallons per day. It's the second largest treatment plant in the facility in the United States. Detroit is the largest at 1.6 billion gallons per day. Wastewater is cleaned to 94% removal efficiency and returned to the water cycle via a 9.5-mile outfall tunnel into Massachusetts Bay. The remaining solids are anaerobically digested and used for provide methane and power, used to generate methane for heat and power generation. The remaining digestate solids are converted to fertilizer pellets. This is a process schematic of the Deer Island treatment system. So we get our flow from 270 miles of collection interceptors from the 43 communities. We have 4 off-island headworks, 1 on-island headworks facility, ranging in size from 125 million gallons per day to 400 million gallons per day. The untreated wastewater is then transported under Boston Harbor through deep rock tunnels. Deer Island draws the wastewater through the tunnels with large pumps on Deer Island, ranging from 600 horsepower to 3,500 horsepower. Deer Island is an activated sludge pure oxygen secondary treatment plant, utilizing sodium hypochlorite for disinfection. This is a clarifier schematic. We had a number of space-saving technologies to be able to fit this much treatment in such a small footprint. So one of the space-saving technologies is stacked clarifiers. This is a design taken from Japan. So we have 48 primary clarifiers that are stacked 1.3 million gallons apiece. And we use 22 of those in dry weather flows, but we need 42 tanks to meet our maximum flows of 1.3 billion gallons per day. So we have quite a bit of redundancy. Our secondary clarifiers are also the same design, around the same volume, but they are not covered. The primary clarifiers are covered, and the air above them is scrubbed to reduce emissions into the atmosphere where we're such close neighbors to Winthrop. The secondary clarifiers, we have 54 of them. We need 51 to treat our maximum secondary flow of 700 million gallons per day. When we reach 700 million gallons per day, that's all we send through secondary. Then we blend primary effluent with secondary effluent prior to disinfection. Anything over 700 million gallons is disinfected and then dechlorinated and sent out through the 9.5-mile outfall. This is an overview of the secondary process, over 900,000 square feet of area covered by our secondary process. In the foreground, you can see 2 white rectangular columns. Those are each one of those is a train for our cryogenic oxygen facility, where we generate our pure oxygen process, where we take ambient outside air and we compress it, we chill it, we purify it, and we rapidly expand it in those rectangular columns. And it reduces the temperature to minus 285 degrees. So the air is separated into gaseous oxygen and nitrogen. The gaseous oxygen is then fed to the secondary process for respiration to do the aerobic biological treatment of the wastewater to remove any of the organic contaminants left over from primary treatment before it goes to disinfection. We have 2 trains capable of 150 tons per day each. We use about 130 tons per day, so we run 1 train. During that process, we also generate some liquid oxygen. That round tank that you see to the right of those white columns is a liquid oxygen storage tank capable of storing 1,000 tons of liquid oxygen. So if we were to have an interruption in the cryogenic process, we can then use that liquid oxygen to vaporize and continue to feed oxygen to our secondary process, so we don't have any treatment upsets. From the secondary reactors, the water goes into secondary clarifiers. Where we allow the biomass to settle out, leaving the clean water to go to disinfection. Some of that biomass is sent back to the reactors to do additional treatment. Some of it is wasted to the residual side of the plant. The wastewater goes on to disinfection, where we add sodium hypochlorite. You can see our large sodium hypochlorite tanks, and to the right bottom of that photo, we have 4 250,000 gallon storage tanks for sodium hypochlorite, and we have 250,000 gallons for sodium bisulfite. So we add the sodium hypochlorite to do the disinfection process, where we need at least 15 minutes of contact time. Then as the water leaves the disinfection basin, it drops into a 420-foot drop shaft, where we turn a hydroturbine generator. We take advantage of that elevation change and turn on a 1 megawatt hydroturbine generator prior to it going out to the outfall. But we also add the sodium bisulfite 870 feet into that tunnel to take advantage of that space for additional disinfection time that we need in our max capacity flows. We have odor control throughout the plant, all the covered tanks, the pump stations, and any of the buildings on Deer Island. The air is scrubbed through wet scrubbers, and then an additional pass through carbon for polishing. We use hydrogen peroxide for odor control also on our influent. As we see hydrogen sulfide levels increase in the summertime, we had peroxide to the influent to reduce those levels coming into the plant so they don't overwhelm our scrubbers. So Deer Island receives about 260 tons of dry tons per solids per day, and about 240 of that makes it to the digesters. The primary sludge is thickened from about 0.5% to 1% to 5 to 7% solids in our gravity thickeners that you can see in the top photograph. We have 6 gravity thickeners that are 70 feet in diameter and about 15 feet deep. And we use 4 of those at a time. So we have 2 spares for redundancy. The secondary sludge is thickened from less than 1% to 5 to 7% in centrifuges. And we have 12 centrifuges. We run probably 6 at a time. The sludge is then combined and co-digested in the anaerobic digesters. The thickened combined sludge is typically 70% primary sludge and 30% secondary sludge. During a typical average flows, with the 260 dry tons per solids, 240 make it to the digesters, but only 100 to 105 tons dry tons per day remained for after the digestion process to be converted to pellets. The rest is converted to methane gas. This is a picture of one of our egg-shaped digesters. We have 12 eggs, a dozen eggs. Typically 8 are in operation at all times. The digesters are 140 feet tall and 90 feet in diameter at their widest point. An empty digester weighs about 720 tons and about 13,500 tons full. So 3 million gallons of sludge weighs over 12,000 tons. We use a methophilic process at 98 degrees. Our mixers are a draft tube center mixer that spans the whole depth of the digester. So we run that mixer at about 15,000 gallons per minute, and that turns over the digester about 7 times per day. I'm sorry, 15,000 RPMs, and turns the digester over 7 times a day. So a lot of mixing. And we have recirculation pumping to provide the heat for the digester as the sludge is coming out. We're reclaiming that heat through heat exchangers. And we're also attached to the primary heating loop from our thermal power plant, where we burn the digester gas. So we generate that flow rate in the heating mixing is between 800 and 1,000 gallons per minute to reheat that sludge and keep that digester at 98 degrees and consistent temperature. The gas production is about 190,000 square cubic feet an hour. We get about 17.5 cubic feet of digas per pound of volatile solids destroyed, and about 65% methane, with a BTU value of 622 BTUs per cubic foot. The egg shape is more efficient than our previous pancake-style digesters, which yielded 15 cubic feet per pound of volatile solids destroyed. With our process, we get about 52 to 55% solids destruction, so we cut our volume in half in the digesters. That's less that we have to make into pellets and find a home for. The rest is turned to gas. About 64% of volatile solids per destruction. We feed about 1.2 million gallons of thickened sludge to the digesters daily in a semi-continuous process. 5,000 gallons per digester, 1 digester at a time, alternating through 4 digesters at a time in each mod. So we have 4 digesters in each mod. We have 3 mods of digesters. We get about a 20-day detention time at this flow rate. We monitor the volatile acids, the alkalinity, and the phosphorus levels. This is a picture from construction. You can see how, if you look around, this is the foundations for the digesters, or the egg carton, if you will, right, where they're going to make their final resting place. If you look around this photo, you can see just how chaotic it was for construction on Deer Island as this place was being put together. It's an amazing feat of how they were able to get all this equipment in such a small space in such a short time frame, right? We did this over 12 years. At its height, Deer Island had 3,500 people working at one time on Deer Island, with over 400 contractors at a burn rate of over $3 million a day. Just unbelievable how many people working on this small site at one time. So this is a picture of the digesters being brought to Deer Island and being offloaded from the barge. The photo on the left is a 1,200-ton, the largest crane in existence, a Lamson crane, moving the digester eggs into their cartons for their final resting spot. The crane needed a team of people to run it. 8 track operators and 2 pilots in the cab, so a large crew to run the crane to pick up the digester and bring it into its place. It would take an entire day to move one digester into place, and slow and steady wins the race when you're picking something this large. Mods 1 and 2 were constructed in New Jersey. So the first 8 digesters were constructed in New Jersey and brought to Deer Island completely assembled. Mod 3 was constructed in Quincy and brought to Deer Island in halves, and the final weld was done on Deer Island. They were designed by MWRA's lead designer, Metcalf and Eddy, during the Boston Harbor project. And the final design for mods 1 and 2 was completed by Black and Veatch, and the shells were constructed by General Dynamics. The final design for mod 3 was done by CDM. The shell was constructed by CBI. So some of our energy benefits with our CHP from anaerobic digestion, we generate annual revenues between 20 and 25 million from our CHP process. We're about 60% off the grid. About 78% of that 60 is the digester gas. We avoid the consumption of over 5 million gallons of number 2 low sulfur diesel fuel to meet the thermal needs of Deer Island. We generate 98% of our thermal needs for all of Deer Island and the digesters. So we supplement in the wintertime slightly with a little bit of fuel oil, as the digester gas is not enough to keep our temperatures up in the colder months. The digester gas is used as a fuel source in a 235 million BTU boiler. We have 2 of those, run one at a time to generate steam, to provide that steam to the heating loop that runs completely around Deer Island to heat the digesters in all 52 buildings on the island. The excess steam is then sent to a 18 megawatt steam turbine generator to generate electricity. This process generates about 22% of the electrical load of Deer Island, approximately 41 million kilowatt hours per year. So we've talked about the process schematic, all of the stuff to the left, and now we're going to go under Boston Harbor to the pelletizing facility. We're going through a 14-inch pipeline, 7 miles to our facility in Fall River, operated by Synagro. So just take a second to talk about our public-private partnership. Synagro has been running our facility since 1991. They do an excellent job of communicating their needs to us. MWRA is responsible for all the capital projects. We work hand in hand with them on a regular basis to make sure that they have everything they need. Projects are being designed on time, and we're getting equipment replaced ahead of any failures. The open lines of communication have been great. Anytime I need information for reporting purposes or any questions, they're always very responsive. And I just wanted to highlight that they do a great job, and a public-private partnership can truly work when both sides communicate efficiently. So this is a basic schematic of their process. So the recycle is fed with the feedstock from the centrifuges, that when the wastewater gets over there, the sludge gets over there, they send it through a centrifuge for complete dewatering. Then it's fed into a stream with the recycle and fed into a dryer. The dryer operates at about 1,500 degrees. Once the pellets come out of and that recycle is integral in forming the pellets and the shape of the pellets. So you need some recycle to get the new sludge to form into pellets. And once the pellets come out of the dryer, they're separated and screened to remove any out-of-spec material and return that via the recycle stream. The cooled pellets are then transported to one of 9 storage silos. before they go out. They're mostly ship by truck. We do have the ability to ship by rail car as well. That can be a challenge in itself to have enough product to ship that way. So this is just a little slide showing our marketing. This slide shows a little bit of a trend that's not typical for a marketing year. We had some molybdenum issues where the molybdenum levels were high. We usually see a spike around the later part of the year, September, October-ish, and then it comes right back down. This past year, it stayed up for a good 5 months and resulted in being over the 40 milligrams per kilogram that's allowed in New York and Massachusetts. So we were unable to distribute it there. Vermont also wouldn't take it because if it doesn't meet spec in your own state, then they won't take it. So it had to be shipped longer distances, which Synagro incurred additional costs for doing that. So being a good public-private partnership, we have provisions in the contract for out-of-spec material. We were able to work together and prove that, what their additional expenses were, and we're able to come to an agreement, and they were reimbursed $195,000 based on the out-of-spec material and having to ship it further. Molybdenum is a chemical used in cooling towers for corrosion control, and the levels were above the 40 milligram per kilogram, causing the material to be out of spec for distribution in New England.
Ed,
Yep.
Kendall's asking a question that's related to this. Do you know what happens with the fluid from the dewatering at Synagro's plant? Is that
Sure.
piped all the way back to you?
Absolutely. So that goes through a pipeline directly to our Braintree Weymouth pump station. Now we get that over whenever they're processing, we get that centrate back, and I'll tell you why that's key a little bit later in the presentation. But yes, that comes back to us without going to any collection system, so they don't need a discharge permit. It's all within the same system to discharge that centrate back to us. This is just another graph of the 2023 results, more typical of our shipping of our distribution of our pellets. This is a project that we did in 2018, I believe, and it was a dryer replacement. So we have 6 trains of dryers. We replaced 3 dryers and a lot of conveyors, a lot of instrumentation and controls, MCCs related to these trains. And it was a very intricate project to do and keep the facility operating and meeting the needs and demands of Deer Island, solids removal while the project was going on. Synagro was instrumental in overseeing the contract, IPC Leiden, and working with Deer Island and MWRA staff to make sure this project went smooth. Truly a great example of how public-private partnership should work in the industry. As you can see, very large rigging of a 30-ton dryer out of this facility was not easy. Based on that photo on the right, you can see how much stuff is in the way and how big of a project that is. So I'll talk a little bit about operational issues as we were getting the pipeline commission, ready to commission, and we were building everything. We had to barge our digested sludge to the Quincy facility and barge the centrate back. This created a number of bottlenecks and operational challenges. All right, so the digested sludge, we needed to thicken that before we put it in the barge, so that we weren't shipping a lot of water. Digested sludge does not like to be thickened. It likes to be dewatered or nothing. So we had 2 digested sludge centrifuges that we would run, one with great capture, making a thicker sludge cake, and then we would run one with very poor capture, so that the mix would blend and we would get something that we wanted that could be pumpable on the delivery to Quincy. The same conversely, we're bringing back that high nutrient load of centrate back to Deer Island on a barge, and we were offloading it as quickly as possible so that we could get that barge filled back up with sludge to send it back to Quincy. So that barge would be unloaded, 800, 900,000 gallons of centrate be unloaded in like 6 hours, causing a huge slug to the treatment process. So this affected our secondary treatment. We resulted in poor settling, caused us to lower our secondary process limit to meet our discharge permit limitations. And we were doing a lot of a lot of more blending outside of rain weather events, so dry weather blending. Even though we were reporting it, we were still, it was still not an acceptable practice. So as time progressed and regulators started to catch up with it and figure out that we were blending more often than rain events, they started to come down on us. But at the same time, we were getting ready to commission the pipeline. So as soon as we commissioned the pipeline, we started pumping the sludge to Quincy and receiving that centrate back over a 24 hours a day, 5-day period versus over 6 hours. All those settling problems went away in secondary treatment, and we were able to get back to our 700 milligallons a day process limit. So a lot of those problems went away with just that pipeline being commissioned.
What was the general timeline of this? Is it in the 80s?
So this was, we started about 96-ish, I believe.
Oh, wow, later than I thought.
91-ish, I believe, and then by early 2000, we had got the pipeline in place. So next we'll talk about struvite, and Deer Island is hooked on ferric. Struvite is a magnesium ammonium phosphate compound that forms hard scale on the inside of pipes that is almost impossible to remove. As you can see from the photo in the top right, that is an overflow line from one of our digesters, almost completely blocked with struvite. So MWRA service area serves a number of coastal communities with I&I challenges, contributing to the high concentrations of magnesium that you see in this chart, 20,000 to 57,000 milligrams per liter coming in our influent. This adds to that formula to help form that struvite, and it accelerates that process where other treatment plants that are not coastal wouldn't have as much magnesium to start forming that struvite. So we needed to treat the struvite with ferric chloride to control the phosphorus levels and prevent the formation of the struvite. So to do that, we do about 2 million pounds of ferric per year at the cost of $4.5 million. The first third of that ferric that we realized when we were doing our testing was first third of that was used to mitigate the hydrogen sulfide levels in the digester gas. So the first third of that 2 million pounds is just for H2S control in our digester gas. The remaining 2/3 reduce the phosphorus levels to a target between 50 and 75 milligrams per liter. This target was developed through testing in the early 2000s. So we stopped to test. We stopped feeding ferric to this process, and we realized that the phosphorus levels were 250 to 300 milligrams per liter. Quickly, we found out that we were getting major blockages of struvite in overflow lines, and the digester gas treatment at the thermal power plant could not keep up with the hydrogen sulfide loading. So we started, and we even found struvite forming in the centrifuges at the pelletizing facility, which is not good, right? So we tried acid washing to remove the struvite with hydrochloric acid. We had glass line piping, and we thought we'd be okay, acid washing the piping. After a couple acid washes, we started seeing pinholes in the piping and started developing leakage. Glass line ductile ion piping is not perfectly lined. There are, imperfections in that lining that the acid was able to find its way through to the piping and cause damage to the outside of the pipe. This resulted in about a $5 million replacements due to that acid washing of the piping replacements for the overflow line system. Well, this is a schematic of our ferric delivery system to make sure that we can feed ferric at all times. We have 3 storage tanks. Each pump can go to any digester at any time. It can be valved to go anywhere it needs to go. And as you can see, we feed at pretty high levels, 42 and 83 gallons per minute. So we can store 35,000 gallons on our facility, and we receive ferric deliveries 5 days a week, about 2 trucks per day. So ferric is very important to us. So now I'll go into talking about the not so flushable wipes. So in our plant, we have scum wells with mixers in them. This picture on the left is a scum well mixer just inundated with rags and inoperable, tripping out, burning out motors, a lot of maintenance headaches. Spend over $1.5 million a year on maintenance for dealing with these flushable wipes. This is a primary clarified gate where the flow comes into the tank almost totally blocked with the rags and other channel issues that we see with floatables and flushable wipes. This is back on the residual side of the plant. This is one of the gravity thickeners. You can see the picture here is a clean gravity thickener. There's the sludge withdrawal well. This is that same piece of equipment, just inundated with rags. And just unbelievable how much we get into the facility. This is a digester mixer being pulled out of the top of the digester, like you see on the right picture with the crane. The rags will make it into the digesters and wind up on the mixers. So it's very expensive and very time consuming to take down a digester to be able to pull this mixer out. We have to transfer all the sludge out of it, keep diluting it until the sludge is at a dilute level where we can drain the digester back to the head of the plant without causing loading issues, making sure it's not generating any more digester gas. Then we have to open it up, get a 300-foot crane in to pull this mixer out. So we developed an operational strategy where we, as I explained earlier, we can mix down, whether we can run the mixer in forward to mix down, or we can run it in reverse to pull liquid up through that center draft tube. So we have a practice once a week. We change direction on the mixer and run it for 8 hours in the opposite direction. And that's helped us to minimize the times that we have to pull the mixer out because of rags. We're pulling them out for maintenance issues and, maintenance reasons and checking on them versus them failing. So that was a great operational strategy by one of our maintenance staff. All right, so we're going to start talking about some capital projects. CDM is our lead engineer on this project. This is to rehab the whole residual side of our plant. So we're gonna take down all the digesters and reline them, redo all the piping, all the pumping that I talked about for the sludge recirculation. All our thick and primary sludge pumps are being replaced. Our gravity thickener overflow pumps, all the controls, everything associated with the residual side of the plant. Preliminary estimates coming in somewhere around $400 million. We're expecting 90% design somewhere in the end of September, beginning of October. It's anticipated to be a 56-month project under their preliminary projected construction schedule. With this project, it's a huge project. So we broke it up into different trades groups as we were doing design meetings. We broke it up into different trades groups, and we had maintenance staff, we had control staff, we had operations staff, and different meetings to make sure that we incorporated all lessons learned throughout the decades of operating this facility on what we didn't want to repeat as we move into the next 30 years, right? So
it's kind of nice to have that opportunity.
Yeah, it was great. Eric and his team did a great job of helping us break down that mammoth of a project into bite-sized pieces. We also did the review of each of those meetings the same way. So they split up the preliminary design report and they sent it to us in sections so that we could review all those sections individually and not have this 500-page document to review all at once. So there was a great way to break down the project and make it digestible, no pun intended, for all the MWRA staff to get a good design report to start with, right? So this is another photo of some of the internal inspection. You see on the right, they're in the boat inside the digester, inspecting it. We've drained it and cleaned it, and we filled it up to the top. We dropped them in at the top and in a boat, and we lowered the level down in integrals as we went down. They inspected the coatings and any internal piping for thickness and any issues that we need to learn, so we could understand what's happening. We can't do all of them, so we're doing a select number to make sure we understand what the condition assessment is, so that we can properly project that into our design and make sure that we take care of everything during construction. Some of the lessons learned incorporated into the design report were we want larger overflow lines to prevent clogging. We want to have piping changes. Right now, we feed our thick and combined sludge to a mod through one thick and combined sludge header. So if we want to drain a digester or take a digester offline in that mod of 4 digesters, we have to stop feeding the entire mod and drain that one digester and then go back to feeding once that digester is drained. So it's very cumbersome, a lot of valve changes. So we want to make it so that we have 2 thick and combined sludge headers. So we want to make it so each digester will connect to both headers. So that way there we can drain an individual digester at a time without stopping the feed to the other 3 in the same mod. And not disrupt operation to any of the digesters. We're adding backup heat exchangers, and mods 1 and 2 were completed first. Mod 3 has 2 heat exchangers that are attached to the primary heating loop to heat that secondary loop that heats the 4 digesters in that mod. So we're adding that second heat exchanger to mods 1 and 2, so we have a backup. Annually, we take them apart to change the ends on the heat exchangers, and anytime we do any work on that heating heat exchanger that's attached to the primary loop, it's like a fire drill to get it back online if it happens in the wintertime, because we don't want to lose the temperature in the digester. So we want to eliminate that urgency and have a backup, have redundancy there to be able to do that project a little more controlled.
General, there's a related question.
Sure.
Is the sludge heating rehab, will MWRA be looking to reduce energy costs? And are there any additional energy efficiency opportunities as part of this project?
So we are committed to decarbonization efforts and in line with Massachusetts. So we are looking at all of that as we get into design. We're still in the preliminary design stage, so we haven't really identified a lot of that yet. But yes, that is on the forefront of our mind, to reduce energy and save on energy wherever we can, reducing our carbon footprint. So with the sludge heating and mixing of the digester, we often struggle in the wintertime. We have 2 pumps for each egg, and we often run both pumps in the wintertime to keep that digester mixed and heated, because our flow rates range from 800 to 1,000 gallons per minute. So we want to go with larger pumps to get to 1,000, 1,200 gallons per minute with 1 pump. So then we still have that redundant pump in reserve if something were to happen to one of those recirculation pumps. We're adding emergency standby generators to the digester mixers to keep them running during any power interruptions. If we get a power interruption, we have to get those mixers back online within 15 or 20 minutes. If not, we start getting that rapid volume expansion. It overwhelms our overflow boxes and starts to come up through our flame arrestor system and starts to come up at the top of the egg. And we don't want that to happen. So we're going to make sure that we have keep those mixers running. We started to look at battery energy storage backup. We're just not there yet, so we have to add the generator for now, and maybe down the line convert that to a battery energy storage system where it's backed up by batteries instead of a generator. We're also looking at containment on the top of the egg, so that if it does start to burp out of the top of the egg, it's contained within the footprint of the top of the digester and doesn't come running down the outside of the digester and create an SSO. We're also replacing the mixing systems in our dye store tanks. Our dye store tanks are our sludge and gas storage tanks. I have a photo later on the presentation of one of those. And shortly after startup, a few years in, the piping system is buried in the bottom in the ground around the bottom of the dye store tanks, and not very serviceable. So shortly after startup, it started to get plugged up with struvite and grit and was unable to be cleaned out. So we haven't been able to mix those tanks in quite some time. So we're going to look forward to getting the ability to mix those tanks again after this project. We're looking at better sampling locations for our operations staff. Right now we have a 1.5-inch line with all that head pressure above it, so it kind of sprays out into a sink, and we want to make that more controlled and more efficient for our operations staff to be able to collect better samples and not be getting sludge on them. We want new style grinder pumps for the thickened primary sludge pumps to deal with a lot of the wipes issues and hopefully reduce the amount of clogging. After a rainstorm, we'll have maintenance over there continuously unplugging pumps, first and second shift. These are some more of our capital projects that are either ongoing or in design. A couple I talked about, but Clarifier rehabilitation project is replacing all the all the gates and all the influent and effluent gates on all of our primary and secondary clarifiers. So each primary clarifier and secondary clarifier have 8 influent gates and 1 effluent gate. So 9 gates per tank, 48 primaries, 54 secondaries, a whole lot of gate work. We're doing coatings work, about 7 football fields worth of coatings work inside these tanks above the water line where the concrete is all degraded. It's a huge project. 296, we're at about $296 million right now from the 289 that we started at. Our cell system pump station, we're replacing all the pumps, piping, valves, VFDs. The whole station is due for an upgrade. So that's projected to be around 200 million. We're in the just finishing the preliminary design report on that project. We have an odor control replacement project that's just about ready to go out for design. That's estimated to be around 150 million. That's all our odor control, all our wet scrubbers, all our carbon scrubbers, all the equipment associated with them, pumps for chemicals, instrumentation and controls. All of it's due for replacement. We're getting to be 30 years old, so. Residual facility, we just talked about that in a little bit more detail. We have off-island headworks that I mentioned in my explanation of the system. We have our Columbus Park and Ward Street headworks facilities that are due for upgrades. One of those 182 million gallon a day capacity, and the other one is 256 million gallons per day capacity. So they're projected to be 150 or $200 million a piece for the upgrade projects. And then Deer Island is going to do a new CHP program. We're in conceptual design right now, where right now we make heat first and then power. So it's inefficient, and we want to switch to a system that will make power first and then heat. So we're going to go to reciprocating engines and generate more electricity before we start worrying about the heat. Still meeting our thermal demands, obviously, but generating a lot more electricity to try to get us, to the high 70s or 80% off the grid. That's pretty much what I have for today. And if you have any questions, be happy to answer any questions. Kind of right on the money there with the 245.
Good job.
45.
Yeah, so there was one question from before that I didn't have an opportunity to get in there. And whoever else has questions, you can just take yourself off mute at this point. But Kendall was asking, he understood that you guys had considered taking pre-slurried organics in the past, like food waste or something. That would definitely get you to 100%. But can you talk a little bit about that? It seems like it got rejected because of logistics, or I don't know.
So we did a study, and you're right, it would be greatly beneficial, especially for our size process. We're located out on the tip of Winthrop, so we can't get material to us very easily. We have a limited number of trucks that we can bring through Winthrop to still be good neighbors, and we have a bunch of chemical deliveries that come in and out here every day. So we can't get the truck traffic in here to bring it to Deer Island. That was the main sticking point.
Oh, well, that's a bummer.
Yeah.
So you need some kind of direct line.
Right. We should have put in a third pipe.
Interesting, yeah. Does anyone else have questions? Go ahead. Hey, I heard that somebody told me you guys have a pilot plant over there.
We do. So when Deer Island was built, we
Does it
have
anaerobic digestion as part of that?
No, it's just the treatment process. But it's a 1 million gallon a day plant that's exactly like the big plant. It's because when they built Deer Island, they didn't have all the staff ready to go. So they had to do an apprenticeship program where they trained staff in this pilot plant to work on the equipment. And it's an exact replica. It's a mini plant of the Deer Island treatment plant.
Wow.
Pretty cool. And
yeah.
the influent comes from the north and south influence, like the big plant. And the discharge goes to the south system. So it doesn't discharge anywhere but inside the plant. So we don't need to worry about a permit or anything like that for it.
Huh. And have you used it to pilot processes in the past, or just for training?
In the past, it was used for process development as well too. Yeah, but process control changes, and if they wanted to try something new, they tried it there first.
Sure. Oh, that's a great thing to have.
Yep.
All right, here's another question for you. Have you incorporated thermal hydrolysis into your process? Do you know anything about the advantages and disadvantages of that, specifically for your operation here?
I'm sorry, I do not.
Okay. That's sort of like the Canby process. Is that what, Melissa? Is that what you're referring to? It definitely can get you more.
I'd love to learn more about it.
Yeah.
Yeah, definitely.
See, Melissa. You could take yourself off mute if you'd like, and if you know something about it, we would all like to know.
Of interest, we looked at Canby or thermal hydrolysis for Deer Island back in, I think it was 2013. And Chad, your digesters were so well run that at the time it didn't make sense to add the process.
See that?
Interesting.
That's a little bit before my time. I was an operator here in 2011, then I left to go to the town of Plymouth, and I came back about 4 years ago. So that was while I was gone, Eric. Thank you for chiming in with that. I appreciate that.
Yeah, hey, you're welcome.
Yeah, thanks, Eric.
Nice to know that we're well run. I believe that that is true.
Oh yeah.
So I'm curious, do you have an iron limit?
We do not. We don't have any.
Because you discharge to the ocean, is that why?
Yep, exactly. We have no nutrients in our permit
The
at all.
thing is, you're hooked on ferric.
Right. It's in our sludge process. So it's after the wastewater leaves the plant. We'd only get it back from a side stream. And it's going into the digester, so.
All right. Anyone else have questions? Like I said, feel free to unmute. Oh, no, go ahead, Matthew, if you want to unmute and ask your question.
First of all, thank you for hosting. Quick question of wondering if there is such an opportunity for academic credit to do any kind of writing for your agency. I'm in a master's degree program for mass communication, so even writing a first draft of something to submit for securing funding for a capital improvement project or a newsletter or blog, if that were an option.
All right. Maybe I can certainly pass on to my contacts there at MWRA.
Mhm.
You're talking about free help for credit?
Yes,
Okay.
Okay, yeah, I'm interested in
Yep.
looking into that as well.
thank you.
All right, thanks, Matthew. Any other questions?
I'm just wondering about that pilot plant again and what else it might be used for besides the two use cases that Chad was talking about.
It's
So,
a 1,000,000 gallons a day pilot plant.
yeah, it's
Good.
the size of a smaller utility, right? I worked in Plymouth. That was a 3 million gallon a day system with 1.5 million influence. So pretty similar size. But right now that plant is not used for anything. It costs over $1 million a year to run it. So it's kind of mothballed in place right now. But
Mm.
you know, it could be used in the future if there was a greater need for, staffing throughout the country. Maybe there could be a program to get it up and running for an operator training ground for sure.
Maybe some experiments on removing PFAS from wastewater.
Yeah, true.
Mm,
Or residuals.
yeah.
Yeah.
Anyway, yeah, so this I learned a lot more than I ever knew about MWRA today.
Well, that's good. I'm glad it was informative.
Yeah, no, thanks so much, Chad. I really appreciate it. And yeah, unless there's any other questions, I want to absolutely thank our sponsor, CDM Smith. Thanks, Eric and crew over there. And thanks to everybody for joining us today. We haven't announced it, but I have Tracy Chouinard from Brown and Caldwell teed up for our next quarterly roundtable. She's the author of one of West's latest textbooks on co-digestion. And so she's going to lead the next roundtable, and I'll get information out to you on that. If you have a good speaker or a topic you'd like to hear about at these roundtables, please email me. Let me know. You can also suggest it on the website with the click of your mouse. So please do that.
Just want to say thank you for inviting me, Janine, and thank you for everyone that came to watch the presentation. And my contact information is on the screen. So if you have any additional questions that you didn't think of today after the fact, please ping me and let's get connected.
I want to thank MWRA for being a great NEBRA member as well. So thanks again for joining us, everyone. Have a great Friday afternoon and a great weekend.
Thanks, you too.
Good job.
Yeah,
Thanks,
Have a good
Janine. Thanks,
weekend.
Chad.
Thank you.
bye, Mark. See ya.